On the vast stage of the cosmos, where invisible forces weave unpredictable trajectories, the classic three-body problem still defies our understanding. In it, the gravitational interaction between three masses reveals chaotic behavior, making it virtually impossible to accurately predict the future. But what if we replace traditional celestial bodies with interstellar visitors, like ʻOumuamua, Borisov, and the recently discovered Atlas, and make Earth our reference point? Are we making an error of judgment? Could this be a new reflection of the ancient human egocentrism that for centuries placed our planet at the center of the universe? After all, who said these bodies are coming to us? What if, on the contrary, we are merely momentarily crossing their orbits, like cosmic dust cutting across ancient paths traced by distant stars? Perhaps they are not visitors at all, but travelers on a path we never considered our destination. Is the sun the true point of attraction? Or are these bodies responding to the gravitational pull of something beyond, of a star we haven't even identified? What are we missing when we insist on seeing ourselves as the center of everything, even in the age of advanced astrophysics? In October 2017, astronomers made a discovery that would shake the foundations of our understanding about the cosmos. An object, later named ʻOumuamua, meaning a messenger from afar arriving first, in Hawaiian, was observed speeding through our solar system. Unlike any comet or asteroid previously detected, ʻOumuamua's trajectory was distinctly hyperbolic, signaling that it was not bound to the sun, and was instead a visitor from another star system. This marked a monumental moment. For the first time, humanity had confirmed the passage of an interstellar object through the neighborhood of our own sun. As the telescopes tracked its movement, ʻOumuamua proved to be full of surprises. Its speed, direction, and the angle at which it entered our solar system all pointed to its foreign origin. But it was the object's behavior as it departed that truly puzzled scientists. Rather than simply following the path dictated by gravity, as most asteroids and comets do, ʻOumuamua accelerated as it left the sun's vicinity. This non-gravitational acceleration was unexpected. Typically, comets display such behavior due to jets of gas and dust erupting from their surfaces as sunlight heats them, a process known as outgassing. Yet, ʻOumuamua showed no visible tail, no cloud of gas or dust, and no detectable release of material. It seemed to defy the known rules of celestial mechanics. The mystery deepened when astronomers analyzed its shape and physical properties. As it tumbled through space, its brightness fluctuated dramatically, suggesting a highly elongated form, perhaps shaped like a cigar or even a flat, disc-like pancake. Some estimates indicated that it could be as much as 10 times longer than it was wide, unlike any natural object observed before. Its surface appeared reddish and highly reflective, adding to the enigma. With limited data and only a brief window to observe, scientists raced to explain what ʻOumuamua might be. Several leading theories emerged. One proposed that it was a fragment of a larger icy body, ejected from its home system after a catastrophic event. Another suggested a hydrogen iceberg, a clump of molecular hydrogen that could sublimate quickly and invisibly, providing the necessary thrust without the telltale signs of a typical comet. Others speculated about a nitrogen-rich crust, similar to Pluto's surface, which could also sublimate in a subtle way. But it wasn't long before more speculative ideas took hold. Avi Loeb, a prominent Harvard astronomer, posited that ʻOumuamua could be artificial in origin, a probe or fragment of alien technology, perhaps sent intentionally or as cosmic debris from a distant civilization. While this idea captured the public imagination and sparked debates about humanity's readiness to recognize signs of extraterrestrial intelligence, most in the scientific community leaned toward natural explanations, underscoring the importance of extraordinary evidence for extraordinary claims. Regardless of its true nature, Oumuamua exposed the limitations of current astronomical technology and observational strategies. Its rapid passage, faster than any previous object entering the solar system, meant observations were brief and incomplete. Yet, this fleeting visit sparked new efforts in astronomy. Projects are now underway to improve early detection of interstellar visitors, and even to one-day launch missions that could intercept and study them up close. In the end, Oumuamua's brief sojourn through our solar system did more than raise questions about its origins. It expanded the boundaries of human curiosity, inviting us to imagine what else might be drifting in the vast expanse between stars. In its wake, astronomers are more vigilant, scanning the skies for the next messenger from afar, ready perhaps to catch a glimpse of the stories carried by these cosmic wanderers. In the vast expanse of our solar system, the unexpected arrival of Borisov in 2019 marked a turning point in our understanding of the cosmos. As the first confirmed interstellar comet, Borisov offered scientists a rare and extraordinary window into the primordial material from another star system. Unlike the enigmatic Oumuamua, whose brief and mysterious passage left more questions than answers, Borisov provided a classic telltale display of cometary behavior. It developed a luminous coma, released gases, and formed a sweeping tail, allowing astronomers to study it in unprecedented detail. The trajectory of Borisov was unmistakably hyperbolic, an unmistakable sign that it was not bound to the gravitational embrace of our sun, but rather was a visitor from the depths of interstellar space. This discovery didn't just prove that objects can cross the vast distances between stars. It also suggested that such interstellar wanderers might be far more common than previously believed, passing unnoticed through our solar system throughout the ages. As telescopes around the world focused on Borisov, new surprises emerged. Detailed spectroscopic studies revealed that this comet contained exceptionally high concentrations of carbon monoxide, far more than typically found in comets native to our own solar system. This chemical fingerprint pointed to its formation in a region of extreme cold, possibly even farther from its home star than the distant Oort cloud is from our sun. The Oort cloud, a vast reservoir of icy bodies at the edge of our solar system, is considered one of the coldest and most remote regions of our celestial neighborhood. Yet, Borisov's makeup hinted at origins in an even more frigid and distant realm. These unique characteristics of Borisov have profound implications for our understanding of planetary system formation. They suggest that the processes shaping comets and other small bodies can vary widely from one star system to another. Each interstellar comet, therefore, carries with it a unique record, a time capsule of the conditions and materials present in the outermost reaches of another solar system. By studying Borisov, astronomers have gained valuable clues about the diversity and complexity of planetary nurseries scattered across the galaxy. Another key distinction between Borisov and its predecessor, Oumuamua, was the opportunity for extended observation. While Oumuamua's swift journey through the solar system allowed only fleeting glimpses, Borisov lingered long enough for scientists to follow its evolution over several months. This allowed for a comprehensive series of observations, enabling researchers to track changes in its brightness, analyze the gases it emitted, and measure the dust particles in its tail. The comet's predictable textbook behavior reinforced existing models of cometary physics, suggesting that the basic processes governing these icy bodies are truly universal. Borisov's visit has also inspired new ambitions for the future of space exploration. Projects like the European Space Agency's Comet Interceptor aim to one-day rendezvous with a pristine comet, possibly even another interstellar traveler, allowing for direct study of materials that have never been altered by the heat and radiation of our sun. Such missions could unlock secrets about the building blocks of planets, the distribution of organic molecules in the galaxy, and the broader story of how planetary systems form and evolve. In the end, Borisov's journey through our solar system was much more than a fleeting astronomical event. It was a profound reminder of the interconnectedness of the universe and of the untold stories carried by the silent wanderers that drift between the stars. Through Borisov, we caught a fleeting glimpse of the far-off places from which it came, and a preview of the discoveries that await as we continue to watch the skies, searching for the next messenger from the interstellar deep. In July 2025, the astronomical community was abuzz with excitement as a remarkable discovery was confirmed. The detection of the interstellar comet 3I Atlas, also catalogued as C 2025 N1 Atlas. Spotted by the Atlas survey system in Chile, this object marks only the third time in history that scientists have observed an interstellar visitor passing through our solar system, following the sensational discoveries of 1I ʻOumuamua in 2017 and 2I Borisov in 2019. Unlike its enigmatic predecessors, 3I Atlas was observed in an active state, with a visible coma, the glowing cloud of gas and dust that surrounds a comet's nucleus, making it far more accessible to study and opening a new chapter in humanity's quest to understand the universe beyond our own solar system. What sets 3I Atlas apart is not just its origin, but its age and journey. Preliminary studies suggest this object may have formed over 7 billion years ago, making it older than our solar system itself. The likely birthplace of this ancient traveler is the thick disk of the Milky Way, a region populated by some of the galaxy's oldest stars. Ejected from its home system by gravitational interactions eons ago, 3I Atlas has wandered the vast interstellar gulfs, untouched and unchanged, until its chance encounter with our cosmic neighborhood. The path of 3I Atlas, traced by astronomers and confirmed by powerful telescopes like the Very Large Telescope in Chile, is hyperbolic, meaning it is not bound to the sun and will eventually leave our system, never to return. Hurtling through space at speeds exceeding 240,000 kilometers per hour, it is on course to make its closest approach to the sun, its perihelion, on October 29, 2025, at a distance of about 1.4 astronomical units, or roughly 210 million kilometers. As it approaches, the comet's increasing brightness and activity will provide a rare window for scientists to observe and analyze the materials that compose it, materials that likely originated in a long-lost solar system. This opportunity is scientifically invaluable. For the first time, astronomers can study the composition of an active interstellar comet in detail, searching for volatile elements and compounds that might reveal clues about its origins. The early detection of its cometary activity, including its forming coma, allows telescopes to capture spectra of the gas and dust it releases. By examining these signatures, scientists hope to identify rare elements or unusual molecular patterns that could betray the unique environmental conditions of its home system, conditions that might differ dramatically from those that shaped the comets of our own solar system. Moreover, the appearance of 3I Atlas strengthens the growing understanding that comets may be the most common type of object ejected from planetary systems across the galaxy. While Oumuamua's odd asteroid-like appearance left many questions unresolved, the clear cometary nature of 3I Atlas supports the idea that icy bodies, rather than rocky ones, are more likely to survive the tumultuous ejection process and traverse the vastness between the stars. The detection of 3I Atlas also has profound implications for the future of space exploration. The realization that our solar system is periodically visited by interstellar objects has spurred interest in developing missions to intercept and study such visitors up close. The European Space Agency's Comet Interceptor mission, set for launch in 2029, is designed precisely with these fleeting opportunities in mind. With each new discovery, like 3I Atlas, the rationale for these ambitious missions grows stronger, promising a future where we might one day sample or even return material from an object born around another star. As we witness 3I Atlas sweep through our skies, we are reminded that our solar system is not an isolated oasis, but a crossroads in the galaxy, a place where ancient wanderers occasionally pass by, bringing with them secrets from the deep past and distant worlds. Each visit is a fleeting gift, and with the tools of modern astronomy, we are now better prepared than ever to learn from these cosmic messengers. The universe may not be coming to us. Perhaps we're just bumping into it by cosmic accident. What other interstellar clues are passing through us without us even realizing it? What if the true story of our place in the cosmos hasn't even begun to be told yet? If these ideas resonate with you, dive deeper with us in The Curious Order. Like, subscribe to the channel and prepare to challenge everything you thought about the movement, origin, and destiny of the universe.